All right, so we've gotten the introduction to regression all sorted out by now. We understand there's a correlation coefficient and a r squared value. Those are important for assessing relationships between two variables, three variables, as many as you like. But there's a couple of rules we need to be assured of to make sure that our regression analysis is valid. There are actually four. Here are the four rules. The first one is you need to establish that there's a linear relationship between the variables you're trying to test. And I'm going to show you how to check whether or not that is the case in this episode today. Next, we need to make sure that the observations are independent of one another, which means that there's not really a correlation between one error and the following error. That's called autocorrelation, and we need to make sure that it doesn't happen. Homoscedasticity is the third rule. We need to make sure that the variance of residuals is constant, and that is a lot of jargon. That sounds pretty complicated, but this was actually my job for one of my quantitative roles, was verifying that our regression analyses did not have heteroscedasticity. Here's a good example. If a share price or if a company does a stock split, the values of their stock is going to half or go into thirds or fourths, depending on what they split it into. So the values that you're regressing on are suddenly drastically changed. So your residuals, which are how incorrect your predictions are based on your regression line, are going to change drastically suddenly in the middle of your analysis. So you need to make sure that throughout the entire analysis, the variance of those residuals is consistent. And number four is the normality of residuals. If we plot a histogram of our errors based on our predicted values, which we can calculate using that y equals mx plus b formula, if we plot those errors and it comes up with a weird shape that's not that standard bell curve, that might be indicative of us trying to fit data into, or trying to fit a model to data that shouldn't be used in linear regression. So that's just a lot of words right now that probably don't make a lot of sense, but we're going to do one episode at a time breaking down each of these four rules. So today, let's get started with testing linearity. I'm going to make a file. It's going to be reg linearity .ipynb. So the file names are always going to be reg underscore for each of the four tests. And then we're going to bring in our same packages from our previous file. So let's go back to our regression analysis to get everything we need. We need to add the target. We also need to add the RSI and regression output. Looks like we can actually just copy this whole thing in for the test. Now, select the environment. And while that loads, we have our model fit to the relative strength index and its relationship to our target, which is the close price change. So if we just run this whole function, we get a couple important pieces of information for conducting this analysis. And we're, again, just like we always do, going to make additional columns to make this intuitive. Now, we have our correlation coefficient and our y-intercept. So we have our formula that we know from algebra, y equals mx plus b. We're going to make a column that creates those values. What is y based on our model? So the correlation coefficient is right here, model.coef underscore 0. So let's return that. Let's make an additional variable. So make coefficient variable coef equals model.coef underscore 0. And I want to return it. Return coef. Coefficient is going to equal generate regression output from the data frame, and return the coefficient and the data frame in our main function. This makes it a bit more complex, but nothing we can't handle. We're returning it in both of these functions. And I also want to return the intercept. So inter equals, if I just make it the complete name. For understandability, we're going to make it the complete name. Intercept equals model.intercept. And that is it. We can now just change a couple things here. Make this coefficient, make this intercept, and return coefficient and intercept. So our coefficient and intercept are going to be what comes from that function. Yeah, our main function isn't going to return all that. We're going to make another function for adding a couple columns to our data frame. So we have the correlation coefficient and this y-intercept from our generate regression output function, but I don't want to return it in our main function because that makes it a bit noisy. And my job is to make this code scalable and understandable for everyone. So that's a little error. Now let's make another function for after we generate the regression output. Define add test linearity. So we're going to test linearity of the data frame with the coefficient that we define, which will be here, and the intercept, which will be here. Awesome. This doesn't look super intuitive immediately. It will later on. So data frame predictions is going to be y, and so let's put the y equals mx plus b formula right here. Y is going to be our predictions column. So we're going to be always trying to predict what value is in this column to start off with. And that is going to be a product of the coefficient. So m is the slope. So we have coef times data frame. And then what it was x? X was our relative strength index. df RSI. And I might take this a step forward. Take this a step forward. Let's call this strategy. RSI. So now we can make this dynamic and keep it as an F string with the strategy plus the intercept that we've defined at the start of the function. And let's return the data frame, and that'll be it. We'll have our predicted values based on our regression model. So data frame is going to equal test linearity. The data frame coef equals the coef we've defined. Intercept is going to equal the intercept we've defined. And that might be complicated. So this coefficient that is going into this function is going to equal this value that comes from a previous function. I might name those differently to make that more understandable. Fit coef, and then intercept is going to be the fit intercept. And fit coef is that, and then fit intercept is what we have here. So this is going to return a coefficient and an intercept. And then the fit coefficient and fit intercept are going to come from that regression output. When I run this whole function, I should see a new column that predicts what those values are going to be based solely on our model. Okay, great. So we have the target value, which is here, and our prediction values are here. We're trying to calculate percent changes, which are pretty small, usually, 0.001. I think I want to multiply both the target and predictions values by 100. Now that I'm taking a closer look at it, I think it'll make more intuitive sense if I do that both for my sake and yours. So when we're calculating the target, multiply by 100. And that should be enough to change both of them. Great. As you can see, that the predicted percent change is generally really small. We can take a look at this by plotting a histogram of all the percent changes. plt.hist, data frame predictions. Let's make sure data frame is equal to main. Yeah, so it's a pretty small range. Usually the predictions are between negative 0.05 and positive 0.15. But that looks great. You can see it's a normal distribution even before we make the bins a bit. Bins equal, let's do 20. Yeah, it's a pretty normal looking distribution, which is nice. So let's get rid of that. Now that we have our predicted values, we need to get our residuals. Our residuals are the difference between the predicted values and the actual values. So what are the residuals? We're going to do this by creating a residuals column. Residuals are sort of a fancy name for errors. How wrong was your model? And you use that in regression analysis almost specifically. So data frame residuals is going to equal data frame predictions minus data frame target. Awesome. And that should be super quick and easy. Now we have our predictions and our residuals. And the way we test linearity is by creating a scatter plot of those two columns. If there is an obvious relationship between what you have predicted and the error that comes with that prediction, then you don't have a linear relationship between the two original variables you were trying to test. So again, I might just sound like I'm saying a lot of words that mean nothing, but I think when we put things into visual plots, it makes a lot more sense really quickly. So information necessary, and now the plot is going to come from this same function. Plot.scatter, which we used in our last episode as well, and it is one of my favorite functions. We need to make a list of data frame predictions and data frame residuals. Should be it. No, I don't need this brackets here. Plot the relationship. And I need to make plt.figure as well, just so we have a separate plot. Interesting. Okay, so we actually have a funneling shape. If I'm going to be picky, there's a little bit of funneling shape here, but for the purposes of our study, this is enough. What you don't want to see is when the predicted value gets greater, the variance gets greater, which as you can see is happening a little bit. There are many observations. Let's take the length of our data frame. It's 8,128. So there's a couple instances where that assumption, where the relationship between those two is violated. The funnel that we see, you would like for it to be less than this, but it's not dramatic enough for it to put a hard stop on continuing this study. If it was, we can address that in a later episode. But for now, we can effectively recognize that we have not violated the first law, at least, of regression analysis. In the next episode, we're going to be testing the second law, which is independence, meaning that these errors are not related with the errors tomorrow. I think it's unlikely that they will be because we're doing percent changes instead of absolute prices. But again, I might be getting ahead of myself, and we're just going to have to run that test tomorrow to make sure it works. So I know this was a bit of a boring episode, and these next ones are going to be. But if you want to understand how to regress effectively, this is important content that people can sometimes charge a lot of money for. So congratulations if you stuck around watching this all for free. You are all the better for it. This four-pronged regression analysis test is super important, and it can take you through a lot of different relationship statistical tests / statistical tests. You know what I mean. Okay. Thanks for watching. See you in the next episode, and stay sharp.